The following is a conversation with Lisa Randall, a theoretical physicist and cosmologist at Harvard. Her work involves improving our understanding of particle physics, supersymmetry, baryogenesis, cosmological inflation, and dark matter. This is the Lex Fridman podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Lisa Randall. One of the things you work on and write about is dark matter. We can't see it, but there's a lot of it in the universe. You also end one of your books with a Beatles song quote, "Got to be good looking because he's so hard to see." What is dark matter? How should we think about it, given that we can't see it? How should we visualize it in our mind's eye?
I think one of the really important things that physics teaches you is just our limitations, but also our abilities. So the fact that we can deduce the existence of something that we don't directly see is really a tribute to people that we can do that. But it's also something that tells you you can't overly rely on your direct senses. If you just relied on just what you see directly, you would miss so much of what's happening in the world. And we can generalize this, but we're just for now to focus on dark matter. It's something we know is there. And it's not just one way we know it's there. In my book, Dark Matter and the Dinosaurs, I talk about the many different ways, there's 8 or 9 that we deduce not just the existence of dark matter, but how much is there. And they all agree. Now, how do we know it's there? Because of its gravitational force. And individually, a particle doesn't have such a big gravitational force. In fact, gravity is an extremely weak force compared to other forces we know about in nature. But there's a lot of dark matter out there. It carries a lot of energy, 5 times the amount of energy as the matter we know that's in atoms, etc. So you can ask, how should we think about it? Well, it's just another form of matter that doesn't interact with light, or at least as far as we know. So it interacts gravitationally, it clumps, it forms galaxies, but it doesn't interact with light, which means we just don't see it. And most of our detection, before gravitational wave detectors, we only saw things because of their interactions with light in some sense.
So in theory, it behaves just like any other matter, it just doesn't interact with light.
So when we say it interacts just like any other form of matter, we have to be careful because gravitationally it interacts like other forms of matter, but it doesn't experience electromagnetism, which is why it has a different distribution. So in our galaxy, it's roughly spherical, unless it has its own interactions. That's another story. But we know that it's roughly spherical, whereas ordinary matter can radiate and clumps into a disk. And that's why we see the Milky Way disk. So on large scales, in some sense, yes, all the matter is similar in some sense. In fact, dark matter is in some sense more important because it can collapse more readily than ordinary matter, because ordinary matter has radiative forces, which makes it hard to collapse on small scales. So actually, it's dark matter that sort of drives galaxy formation, and then ordinary matter kind of comes along with it. And there's also just more of it. And because there's more of it, it can start collapsing sooner. That is to say, the energy density in dark matter dominates over radiation earlier than you would if you just had ordinary matter.
So it's part of the story of the origin of a galaxy, part of the story of the end of the galaxy, and part of the story of all the various interactions throughout.
Exactly. I mean, in my book, I make kind of sort of jokes about, it's like when we think about a building, we think about the architect, we think about, the high level, but we forget about all the workers that did all the grunt work. And in fact, dark matter was really important in the formation of our universe, and we forget that sometimes.
So that's a metaphor on top of a metaphor. Okay. the unheard voices that do the actual work. Okay.
Exactly. No, but it is a metaphor, but it also captures something, because the fact is we don't directly see it, so we forget it's there, or we don't understand it's there, or we think it's not. The fact that we don't see it makes it no less legitimate. It just means that we have challenges in order to find out exactly what it is.
Yeah, but the things we cannot see that nevertheless have gravitational interaction with the things we can see is at the layman level is just mind-blowing,
It is and it isn't, because I think what it's teaching us is that we're human. The universe is what it is. And we're trying to interact with that universe and discover what it is. We've discovered amazing things. In fact, I would say it's more surprising that the matter that we know about constitutes as big a fraction of the universe as it does. I mean,
Mm-hmm.
we're limited, we're human.
Mm-hmm.
And the fact that we see 5% of the energy density of the universe, about 1/6 of the energy density of matter, that's kind of remarkable. I mean, why should that be? There could be anything could be out there. Yet the universe that we see is a significant fraction.
Yeah, but a lot of our intuition, I think, operates using visualizations in the mind.
That's absolutely true. And it's certainly writing books. I realized also how many of our words are based on how we see the world. And that's true. And that's actually one of the fantastic things about physics is that it teaches you how to go beyond your immediate intuition to develop intuitions that apply at different distances, different scales, different ways of thinking about things.
Yeah, how do you anthropomorphize dark matter?
I just did, I think. I made it the grunt workers.
Oh yeah, that's good. Yeah, you did. Yeah, that's why you get paid the big bucks and write the great books. Okay, so you also write in that book about dark matter having to do something with the extinction events, the extinction of the dinosaurs, which is kind of a fascinating presentation of how everything is connected. So I guess the disturbances from the dark matter, they create gravitational disturbances in the Oort cloud at the edge of our solar system, and then that increases the rate of asteroids hitting Earth.
So I want to be really clear. This was a speculative theory.
Mm-hmm. I love it though.
I mean, and I liked it too. And we still don't know for sure, but what we liked about it. So let me take a step back. So we usually assume that dark matter is we being physicists, that it's just one thing. It's just basically non-interacting aside from gravity or very weakly interacting matter. But again, we have to get outside this mindset of just humans and ask what else could be there. And so what we suggested is that there's a fraction of dark matter, not all the dark matter, but some of the dark matter, maybe it has interactions of its own. Just the same way in our universe, we have lots of different types of matter. We have nuclei, we have electrons, we have forces. We have lots of. It's not a simple model, the standard model, but it does have some basic ingredients. So maybe dark matter also has some interesting structure to it. So maybe there's some small fraction. And the interesting thing is that if some of the dark matter does radiate, and I like to call it dark light because it's light that we don't see, but dark matter would see. It could radiate that, and then it could perhaps collapse into a disk the same way ordinary matter collapsed into the Milky Way disk. So it's not all the dark matter, it's a fraction. But it could conceivably be a very thin disk of dark matter, thin, dense disk of dark matter. And so then the question is, do these exist? And people have done studies now to think about whether they can find them. I mean, it's an interesting target. It's something you can measure. By measuring the positions and velocities of stars, you can find out what the structure of the Milky Way is. But the fun proposal was that the solar system orbits around the galaxy. And as it does so, it goes a little bit up and down, kind of like horses on a carousel. And the suggestion was every time it goes through, you have an enhanced probability that you would dislodge something from the edge of the solar system in something called the Oort cloud. So the idea was that at those times, you're more likely to have these cataclysmic events, such as the amazing one that actually caused the last extinction that we know of for sure.
It wasn't so amazing for the dinosaurs.
Or for 2/3 of the species on the planet.
Yeah, but it gets amazing for humans. We wouldn't be.
What really is amazing, I mean, I talk about this in Dark Matter and the Dinosaurs. It's just an amazing scientific story because it really is one of the real stories that combine together different fields of science. Geologists at the time, or, people thought that things happened slowly and this would be a cataclysmic event. And also, I have to say, if you think about it, it sounds like a story like a 5-year-old would make up. Maybe the dinosaurs were killed by some big rock that came and hit the earth. But then there really was a scientific story behind it. And that's also why I like the dark disk, because there's a scientific story behind it. So as far-fetched as it might sound, you could actually go and look for the experimental consequences or the observational consequences to test whether it's true.
I wish you could know like high resolution details of where that asteroid came from, like where in the Oort cloud, why it happened. Is it in fact because of dark matter? Just like the full tracing back to the origin of the universe. Because humans seem to be somewhat special, but it seems like so many fascinating events at all scales of physics had to happen for
So
humans to
I'm
come from.
really, really glad you mentioned that, because actually that was one of the main points of my book, Dark Matter and the Dinosaurs. One of the reasons I wrote it was because I really think we are abusing the planet. We're changing the planet way too quickly. And just like anything else, when you alter things, it's good to think about the history of what it took to get here. And as you point out, it took many operations on many different scales. We had to have the formation of structure, the formation of galaxies, the formation of the solar system, the formation of our planet, the formation of humans. I mean, there's so many steps that go into this. And humans, in some part, were the result of the fact that this big object hit the earth, made the dinosaurs go extinct, and mammals developed. I mean, it is an incredible story. And yes, something else might come of it, but it won't be us if we mess with it too much.
But it is on a grand scale. Earth is a pretty resilient system. Can you just clarify? It's just fascinating. The shape of things. So the shape of the Milky Way of the observable stuff is mostly flat. And then you said dark matter tends to be spherical, but a subset of that might be a flat disk.
So you want to hear about the shape of things.
Yes, yes, please.
So structure formed early on, and now our structure that we live in is, so we know about the Milky Way galaxy.
Mhm.
So the Milky Way galaxy has the disk you can see in a dry, dark place. That's where stars and light is. But you can also measure, in some ways, the dark matter. And we believe that dark matter is more or less spherically distributed. And like we said, there's a lot of it. Not necessarily in the disk, but just because it's a sphere, there's a lot of it sitting there. And the reason it doesn't collapse, as far as we know, is that it can't radiate the same way. So because it can radiate, ordinary matter collapses. And it's actually because of conservation of angular momentum, it stays a disk and it doesn't just collapse to the center. So our suggestion was that maybe there are some components of dark matter that also radiate. Like I said, that's far from proven. People have looked for disks. They see some evidence of some disks of certain densities. But
I see.
these are all questions that are worth asking. Basically, if we can figure it out from existing measurements, why not try?
Okay, so there's not all dark matter is made the same. This is
Well, that's a possibility.
Right.
We actually don't know what dark matter is in the first place. We don't know what most of it is. We don't know what a fraction is. I mean, it's hard to measure. Why is it hard to measure? For exactly the reason you said earlier, we don't see it. So we want to think of possibilities for what it can be, especially if those give rise to some observational consequences. I mean, it's a tough game because it's not something that's just there for the taking. You have to think about what it could be and how you might find it.
And the way you detect it is gravitational effects on things we can see.
That would be the way you detect the type of dark matter I've been talking about. People have suggestions for other forms of dark matter. They could be particles called axions. They could be other types of particles. And then there are different ways of detecting it. I mean, the most popular candidate for dark matter, probably until pretty recently because they haven't found it, is something called WIMPs, weakly interacting massive particles. Particles that have mass about the same as the Higgs boson mass. And it turns out then you would get about the right density of dark matter. But then people really like that, of course, because it is connected to the standard model, the particles that we know about. And if it's connected to that, we have a better chance of actually seeing it. Fortunately or unfortunately, it's also a better chance that you can rule it out because you can look for it. And so far, no one has found it. We're still looking for it.
Is that one of the hopes of the Large Hadron Collider?
That was originally one of the hopes of the Large Hadron Collider. I'd say at this point, it would be very unlikely given what they've already accomplished.
Mhm.
But there are these underground detectors, xenon detectors that look for dark matter coming in, and they are going to try to achieve a much stronger bound than exists today.
Just take that tangent. Looking back now, what's the biggest, to you, insight to humanity that the LHC has been able to provide?
It's interesting. It's both a major victory. The Higgs boson was proposed 50 years ago, and it was discovered. The Higgs mechanism seemed to be the only way to explain elementary particle masses, and it was right. So on the one hand, it was a major victory. On the other hand, I've been in physics long enough to know it was also a cautionary tale in some sense, because at the time I started out in physics, we had proposed something in the United States called the superconducting supercollider. A lot of physicists, I'll say particularly in Europe, but I'd say a lot of physicists were sanguine that the Large Hadron Collider would have the energy reach necessary to discover what underlies the Standard Model. We don't want to just discover the Standard Model. We want to know what the next step is. And I think here, people were more cautious about that. They wanted to have a more comprehensive search that could get to higher energies, more events, so that we could really more definitively rule it out. But in that case, many people thought they knew what would be there. It happened to be a theory called supersymmetry. So a lot of physicists thought it would be supersymmetry. I mean, it's one of the many factors, I think, that went into the fact that the Large Hadron Collider became the only machine in town. And the superconducting supercollider would have just been if it really had achieved what it was supposed to, would have been a much more robust test of the space. So I'd say for humanity, it's both a tribute to the ability of discovery and the ability of really believing in things so that you have the confidence to go look for them. But it's also a cautionary tale that you don't want to, assume things before they've been actually found. So you want to do things you want to believe in your theories, but you also want to question them at the same time in ways that you're more likely to discover the truth.
But it's also an illustration of grand engineering efforts that humanity can take on, and maybe a lesson that you could go even bigger.
I'm really glad you said that, though, too, because that's absolutely true. I mean, it really is an impressive. It's impressive in so many ways. It's impressive technologically. It's impressive at engineering level. It's also impressive that so many countries work together to do this. It wasn't just one country, and how it was also impressive in that it was a long-term project that people committed to and made it happen. So it is a demonstration that when people set their minds to things and they commit to it, that they can do something amazing.
But also in the United States, maybe a lesson that bureaucracy can slow things down. To where
bureaucracy and politics and economics, many things can make them faster and make them slower.
So science is the way to make progress. Politics is the way to slow that progress down. And here we are.
Well, I don't want to overstate that, because without politics, the LHC wouldn't happen either. So, but
you need broccoli.
But sometimes I do think. I mean, you're not asking this question, but sometimes I do think when I think about some of these conflicts, sometimes it's just good to have a project that people work on together. And there were some efforts to do that in science too, to have Palestinians and Israelis work together. A project called Sesame. I think it's not a bad idea when you can do that. When you can get, sort of forget the politics and just focus on some particular project. Sometimes that can work.
Some kind of forcing function, some kind of deadline that gets people to sit in a room together, and you're working on a thing, but as part of that, you realize the common humanity, that you all have the same concerns, the same hopes, the same fears, that you are all human. And that's an accidental side effect of working together on a thing.
That's absolutely true. And it's one of the reasons CERN was formed, actually. It was post-World War II, and a lot of European physicists had actually left Europe, and they wanted to see Europeans work together and sort of rebuild. And it worked. I mean, they did. And it's true. I often think that one of the major problems is we just don't meet enough people, so that everyone seems like when they seem like the other, it's more easy to forget their humanity. So I think it is important to have these connections.
Given the complexity, all cosmological scales involved here that led to the extinction of the dinosaurs, when you look out at the future of Earth, do you worry about future extinction events?
I do think that we might be in the middle of an extinction right now, if you define it by the number of species that are getting killed off. And it's subtle, but, it's a complex system. The way things respond to events is sometimes things evolve. Sometimes animals just move to another place. And the way we've developed the Earth, it's very hard for species just to move somewhere else. And we're seeing that with people now too. I mean, I know people are worried just about AI taking over, and that's a totally different story. We just don't think about the future very much. We think about what we're doing now. And we certainly don't think enough about all the animals that we're destroying, all the things that are precursors to humans that we sort of rely on.
It's interesting to think whether the things that threaten us is the stuff we see that's happening gradually, or the stuff we don't really see that's going to happen all of a sudden. I sometimes like think about what should we be more worried about, because it seems like with the asteroids or nuclear war, it could be stuff that just happens one day. When I say one day, meaning over a span of a few days or a few months, but on a not on a scale of decades and centuries. Because we sometimes mostly talk about stuff that's happening gradually, but we can be really surprised.
It's actually really interesting. And that was actually one of the reasons it took a while to determine what it was that had caused the last extinction, because people did think at the time, many people thought that things were more gradual. And the idea of extinction was actually a novel concept at some point.
Mm-hmm.
I mean, these aren't predictable events necessarily; they're only predictable on a grand scale. But sometimes they are, and I think people were pretty aware that nuclear weapons were dangerous. I'm not sure people are as aware now as they
Yeah.
were, say 20 or 30 years ago, and that certainly worries me. Um, I have to say I was not as worried about AI as other people, but now I understand. And it's not. I mean, it's more that as soon as you create things that we lose control over, it's scary. And the other thing that we're learning from the events today is that it takes a few bad actors. It takes everyone to sort of make things work well. It takes not that many things to make things go wrong. It's the issue with disease. We can find out what causes a disease, but to make things better is not necessarily that simple. Sometimes it is, but for things to be healthy, a lot of things have to work.
Mhm.
For things to go wrong, only one thing has to go wrong. And so it's amazing that we do it. And the same is true for democracy. For democracy to work, a lot of people have to believe in it. A few bad actors can destroy things sometimes. So a lot of the things that we really rely on are delicate equilibrium situations. And there is some robustness in the systems. We try to build in robustness, but a few extreme events can sometimes alter things. And I think that's what people are scared of today in many ways. They're scared of it for democracy. They're scared of it for peace. They're scared of it for AI. I think they're not as scared as they should be about nuclear weapons, to be honest. I think that's a more serious danger than people realize. Um, I think people are a little bit more scared about pandemics than they were before. But I still say they're not super scared about it. So you're right. There are these major events that can happen, and we are setting things up so that they might happen. And we should be thinking about them. The question is, who should be thinking about them? How should we be thinking about them? How do you make things happen on a global scale? Because that's really what we need.
It certainly shouldn't be a source of division. It should be a source of grand collaboration, probably.
Wouldn't that be nice?
Yeah. I just wonder what it'd be like to be a dinosaur. It must have been beautiful to look at that asteroid just enter the atmosphere until everything just man, that would be one of the things I would travel back in time to. It's just to
That's also
watch it.
one of the things that I think you probably could do with virtual reality. I don't think you have to be there and get extinct.
To just experience it.
I think there's something, it's an event, you're just watching, you're not doing anything, you're just looking at it. So maybe you could just recreate it.
I actually heard that there's a nuclear weapon explosion experience in virtual reality that's good to remind you about what it would feel
I
like.
have to say, so I got an award from the Museum of Nuclear History and Technology in the Southwest. And I went to visit the museum, which turned out to be mostly a museum of nuclear weapons. And the scary thing is that they look really cool.
Yeah.
It's true that you have that, yes, this is scary, but you also have this is cool feeling. And I think we have to get around that because, I kind of think that, yes, you can be in that, but I'm not sure that's going to make people scared. Have they actually asked afterwards? Are you more or less scared?
Yeah. That's a good, it's a really good point. I mean, that's a good summary of just humanity in general, where attracted to creating cool stuff, even though it can be dangerous.
And actually, that was the really interesting thing about visiting that museum. Actually, it was very nice because I had a tour from people who had been working there in the Cold War, and actually one or two people from the Manhattan Project. It was a very cool tour. And you just realize just how just the thing itself gets you so excited. I think that's something that sometimes these movies miss. Just the thing itself, you're not thinking about the overall consequences. And it was kind of like, in some ways, it was like the early Silicon Valley. People were just thinking like, what if we did this? What if we did that? And not keeping track of like what the peripheral consequences are. And you definitely see that happening with AI now. I mean, I think that was the moral of the battle that just happened. That it's just full speed ahead.
Which gives me a really great transition to another quote in your book. So you write about the experience of facing the sublime in physics, and you quote Rainer Rilke, quote, "For beauty is nothing but the beginning of terror, which we are still just able to endure, and we're so awed because it serenely disdains to annihilate us." It's pretty intense. It, I think, applies to nuclear weapons.
But it also, I mean, at a more mundane, perhaps, level, I think it applies, it's really interesting. One of the things I found when I wrote these books is, some people love certainty. Scientists many revel in uncertainty. It's not that you want to be uncertain, you want to solve it. But you're at this edge where it's really frustrating because you don't really want to not know the answer. But of course, if you knew the answer, it would be done. So you're always at this edge where you're trying to sort things out. And there is something scary. You don't know you don't know if there's going to be a solution. You don't know if you're going to find it. So it's not something that can destroy the earth. It's just something that you do on your individual level. But then, of course, there are much bigger things like the ones you're talking about where they could actually be dangerous. The stuff I do, I just want to be clear, I'm doing theoretical physics, not very dangerous. But sometimes things end up having bigger consequences than you think.
Yeah, but dangerous in a very pragmatic sense. But isn't it still in part terrifying when you think of just the size of things, like the size of dark matter, like the power of this thing in terms of its potential gravitational effects, just this cosmological objects of a black hole at the center of our galaxy.
So this might be why I'm a physicist or why I differ from other people.
Yeah.
Because I'm not such a big fan of humanity in some ways. Some ways I am. But the idea that we were everything would be really boring to me. I love the idea that there's so much more out there, that there's a bigger universe and there's lots to discover and that we're not all there is. Wouldn't it be disappointing if we were all there is? Yeah,
and the full diversity of other stuff. It's pretty interesting.
We have no idea how much there is. We know what we can observe so far. So the idea that there's other stuff out there that we yet have to figure out, it's exciting.
Well, let me ask you an out there question.
Uh-oh.
Okay. So if you think of like humans on Earth, life on Earth, as this pocket of complexity that emerged, and there's a bunch of conditions that came to be, and there's Darwinian evolution, and however life originated. Do you think it's possible there's some pockets of complexity of that sort inside dark matter that we can't see?
So that's possible.
Mm-hmm. Chemistry and biology evolving in different ways.
And that's one of the reasons we suggest. I mean, it's not the reason, but it would be true if there were the type of interactions we suggest. I mean, it would need more complex ones. And we don't know. I will say that the conditions that give rise to life and complexity, they're complex, they're unlikely. So it's not like there's great odds that would happen, but there's no reason to know that it doesn't happen. It's worth investigating. Are there other forces that exist in the dark matter sector? That's exactly.
So the dark matter sector doesn't have all the forces of the standard model of physics?
Right. As far as we know, it doesn't have any. It might have it at some low level, but it could have its own forces, just like the dark matter might not experience our light. Maybe it has its light that we don't experience.
So there could be other kinds of forces.
I mean, there could be other kinds of forces even within our sector that are too weak for us to have discovered so far, or that exist at different scales than we know about. I mean, we detect what interacts strongly enough with our detectors to detect. So it's worth asking. And that's one of the reasons we build big colliders, to see, are there other forces, other particles that exist, say, at higher energies, at shorter distance scales than we've explored so far. So it's not just in the dark matter sector, even in our sector, there could be a whole bunch of stuff we don't yet know.
So maybe let's zoom out and look at the standard model of particle physics. How does dark matter fit into it? First of all, what is it? Can you explain what the standard model is?
So the standard model of particle physics is basically, tells us about nature's most basic elements and their interactions. And so it's the substructure as far as we understand it. So if you look at atoms, we know they have nuclei and electrons. Nuclei have protons and neutrons in them. Protons and neutrons have particles called quarks that are held together by something called the strong force. They interact through the strong force, the strong nuclear force. There's something called the weak nuclear force and electromagnetism. So basically, all those particles and their interactions describe many, many things we understand. That's the standard model. We now know about the Higgs boson, which is associated with how elementary particles get their mass. So that piece of the puzzle has also been completed. We also know that there are kind of a weird array of masses of elementary particles.
Mhm.
There's not just the up and down quark, but there are heavier versions of the up and down quark, charm and strange, top and bottom. There's not just the electron, there's a muon and a tau. There are particles called neutrinos, which are under intense study now, which are partnered with the leptons through the weak interactions. So we really do know these basic elements. And we know the forces, we know, I mean, when we're doing particle physics experiments, we can usually even ignore gravity, except in exceptional cases that we can talk about. So those are the basic elements in their interactions. Dark matter stands outside that. It's not interacting through those forces. So when we look at the world around us, we don't usually see the effects of dark matter. It's because there's so much of it that we do, and it doesn't have those forces that we know about. But the standard model has worked spectacularly well. It's been tested to a high degree of precision. People are still testing it. And one of the things we do as physicists is we actually want it to break down at some level. We're looking for the precision measurement or the energy or whatever it will take where the standard model is no longer working. Like, not that it's not working approximately, but we're looking for the deviations. And those deviations are critical because they can tell us what underlies the standard model, which is what we really want to see next.
Where can you find the places where the standard model breaks down? Like, what are the places you can see those tiny little deviations?
So we don't know yet, but we know the kinds of things you would want to look for. So one obvious place to look is at higher energy. We're looking at the Large Hadron Collider, but we'd love to go beyond that. Higher energies means shorter distances, and it means things that we just couldn't produce before. I mean, E equals mc squared. So if you have a heavy particle and you don't have enough energy to make it, you'll never see it. So that's one place. The other place is precision measurements. The standard model has been tested exquisitely. So if it's been tested at 1%, you want to look at 0.1%. Mm-hmm. And there are some processes that we know shouldn't even happen at all in the standard model or happen at a very suppressed level. And those are other things that we look for. So all of those things could indicate there's something beyond what we know about, which of course would be very exciting.
When you just step back and look at the standard model, the quarks and all the different particles and neutrinos, and isn't it wild how this like little system came to be and underpins everything we see?
Absolutely. And that's why we'd like to understand it better. We want to know, is it part of some bigger sector? Why are these particles, why do they have the masses they do?
Yeah.
Why is the Higgs boson so light compared to the mass it could have had, which we might have even expected based on the principles of special relativity and quantum mechanics? So that's a really big question. Why are they what they are?
And they originate, there's like some mechanism that created the whole thing?
That's one of the things we're trying to study. Why is it what it is?
I mean, even just like the mechanism that creates stuff. Like the way a human being is created from a single cell. It's like embryogenesis, like the whole thing, like you build up this thing. All of it, this whole thing comes to be from just like a
Well,
tiny
don't forget,
little...
it is interacting with the environment.
Sure. Okay. Right. It's not. Right.
It's important.
Well, that's a really good question. Is how much of it is the environment? Is it just the environment acting on a set of constraints, and like how much of it is just the information in the DNA or the information? How much is it in the initial conditions of the universe, or versus the some other thing acting on it?
These are big questions. These are big questions in pretty much every field. Um, we for the universe, we do consider it. It's everything there is by definition.
Mhm.
But people now think about it as it one of many universes. And of course, it's a misnomer. But could there be other places where there are self-contained gravitational systems that we don't even interact with? So, but those are really important questions. And the only way we're going to answer them is, we go back as far as we can. We try to think theoretically, and we try to think about observational consequences. That's all we can do.
One interesting way to explore the standard model is to look at your fun, nuanced disagreement with Carlo Rovelli. When you talked about him writing in his book, electrons don't always exist. They exist when they interact. They materialize in a place when they collide with something else. And you wrote that, well, I'll just read the whole thing because it's kind of interesting. Stocks may not achieve a precise value until they're traded, but that doesn't mean we can't approximate their worth until they change hands. Similarly, electrons might not have definite properties, but they do exist. It's true that the electron doesn't exist as a classical object with definite position until the position is measured, but something was there, which physicists use a wave function to describe. It's a fascinating, nuanced disagreement. So, do electrons always exist or not? Does a tree fall in the forest if nobody's there to see it?
So I like to think of the universe as being out there, whether or not. I mean, it would be really weird if the only time things came into existence was when I saw them or I measured them.
There's a lot of weird stuff.
I could believe that the Middle East doesn't exist because I'm not there now.
Yeah.
That would be kind of ridiculous. I think we would all agree on that. So I think there's only so much that we can attribute to our own powers of seeing. So, and the whole system doesn't come into being because I'm measuring it. And so what is weird, and this isn't even a disagreement about the standard model, this is a disagreement about how you interpret quantum mechanics. I would say that those wave functions are real. One of the things that, don't forget, that particle physics does, that quantum field theory says, is that electrons can be created and destroyed. It's not that every electron has to be in the universe. There can be, that's what happens at colliders. Particles get created and destroyed. But that doesn't mean that if I have an electron in an atom, it's not there. It's certainly there, and we know about it. Its charge is there.
So physics is a kind of way to see the world. So what at the bottom, what's the bottom turtle? Like, what do you have a sense that there's a bottom reality that we're trying to approximate with physics?
I think we always have in our head maybe that we'd like to find that, but I might not seem so, but I think I'm kind of more humble than a lot of physicists. I'm not sure that we're ever going to get to that bottom level, but I do think we're going to keep penetrating different layers and get further.
I just wonder how far away we are,
We all wonder that. It's not even what's even the measure of how far away we are. One way you can measure it is just by our everyday lives. In terms of our everyday lives, we've measured everything. In terms of what underlies it, there's a lot more to see. And so part of it has to do with how far we think we can go. It might be that the nature of reality changes so much that even these terms are different. Maybe we'll measure, the notion of distance itself might break down at some point.
But also to push back on the we've measured everything. Maybe there's stuff we haven't even considered as measurable. For example, consciousness, or there might be stuff, just like you said, forces unseen, undetected.
So it's an interesting thing. So and this is often a confusion that happens. So there's sort of the fundamental stuff underlying it. And then there's sort of the higher levels, what we'll call like an effective theory at some level. So we're not always working. When I throw a ball, I don't tell you where every atom is. I tell you there's a ball. And so there might be different layers of reality that are built in terms of the matter that we know about, in terms of the stuff we know about. And when I say we've measured everything, I say that with a grain of salt. I measure,
of course,
everything about the standard model. So there's lots of phenomena that we don't understand, but often they're complex phenomena that will be given in terms of the fundamental ingredients that we know about.
But that is an interesting question because, yes, there's phenomena that are at the higher level of abstractions that emerge, but maybe, like with consciousness, there is far out people that think that consciousness is panpsychist, right? That there's going to be almost like a fundamental force of physics that's consciousness that permeates all matter, right?
I mean, usually when you have when you have a far out theory,
Yes.
the thing you do is you test all the possibilities within the constructs that exist.
Yeah.
So you don't just jump to the most far out possibility. I mean, you can do that, but then to see if it's true, you either have to find evidence of it or you have to show that it's not possible without that. And we're very far from that.
I think one of the criticisms of your theory on dinosaurs was that it requires, if I remember correctly, for dark matter to be weirder than it already is. And then I think you had a clever response to that. Can you remind?
I'm not sure I remember what I said then, but I mean, we have no idea how weird dark matter is. I mean, it's based on everyone thinking they know what dark matter is. I mean, so weirder than it already is. I mean, it's not already anything. We don't know what it is. So there's no normalization here.
So dark matter, do we know that if dark matter varies in density?
It certainly does in the universe, so for example, there's more dark matter in galaxies than there is between galaxies. So it clumps. I mean, it's matter. So it's distributed like matter. It is matter.
So it does clump. But the full details of how it clumps and the complexity of the clumping.
It's understood pretty well. People do simulations. Where people are always looking for things, including us as particle physics, is sort of at small scales. Are there deviations on small scales, so that indicating other interactions or other processes, or interactions with baryons, that is to say, normal matter that we don't understand. But on large scales, we have a pretty good understanding of dark matter distribution.
You were part of a recent debate on, quote, can science uncover reality? Let me ask you this question then. What do you think is the limits of science?
I'm smart enough to know I have no idea. And also, it's not even clear what science means, right? Because there's the science that we do, which is particle physics. We try to find fundamental things and figure out what their effects are. There's science like biology where, it's at a higher level. The kind of questions you ask are different. The kind of measurements are different. The kind of science that's going to happen in the sort of more numerical age, or even AI, or like, what does it mean to answer a question? Does it mean that we can predict it? Does it mean that we can reproduce it? So I think we're coming up against sort of the definition of what we mean by science as human beings. So in terms of the science that we can do, I don't think we'll know it until we get there. We're trying to solve hard problems, and we've made progress. I mean, if you think of how much science has advanced in the last century or century and a half, it's incredible. I mean, we didn't even know the universe was expanding at the beginning of the 20th century. We didn't know about quantum mechanics at the beginning of the century. We didn't know about special relativity. That's a lot in a relatively short time, depending on how you think of time. So I think it would be premature to say we know the limitations.
And at various points throughout that history, we thought we solved everything, or declared, or at least various people.
Where we was various people, exactly.
Yeah. Declared that we've solved everything. So this is also a good place to maybe, could you describe the difference between top-down and bottom-up approaches to theoretical physics that you talked about in the book?
So you could try to jump in and say, I have a theory that I think is so perfect that I can predict everything from it, or at least predict some salient features from it.
That's top-down.
That would be top-down. Bottom-up is more like, like the questions we just asked. Like, why are masses what they are? We measure things. We want to put them together. And usually a good approach is to combine the two. If you ask a very specific question, but combine it with the methods of knowing that there could be a fundamental theory underlying it, sometimes you make progress. I mean, the community tends to get segmented or fragmented into people who do one or the other. But there are definitely times, some of my best collaborations have with people who are more top-down than I am, so that we come up with interesting ideas that we wouldn't have thought of if either one of us was working individually.
Would you say the truly big leaps happen top-down, like Einstein?
Einstein was not a top-down person in the beginning. He was, Special relativity was very much him thinking about, they were thought experiments, but he was very much, the original theory about relativity is something like on the nature of electromagnetism. He was trying to understand how Maxwell's laws could make sense when they were, seemed to have different symmetries than what we had thought they were. So he was very much a bottom up person. And in fact, he resisted top down for a long time. Then when he tried to do the theory of general relativity or the general theory of relativity, whichever you want to call it, incorporating gravity into the system where you need some feedback, then he was helped by a mathematician who had developed some differential geometry and helped him figure out how to write down that. And after that, he thought top down was the way to go, but he actually didn't make that much progress. But certainly, so I think it's, naive to think it was just one or the other. In fact, a lot of people who made real progress were rooted in actual measurements.
Well, speaking of mathematicians, what to you is the difference, because you've had a bit of foot in both, between physics and mathematics in the way it helps us understand the world?
Well, to be frank, there's a lot more overlap in physics and math, I think, than has been. I mean, well, maybe not more, but there's certainly a lot. But I think, again, the kinds of questions you're asking are usually different. Mathematicians like the structure itself.
Mm-hmm.
Physicists are trying to concentrate on, to some extent, on the consequences for the world. But there is a lot of overlap.
The string theory is an example. There's certain theories where there's a certain kind of mathematical beauty to it.
There's also some really cool ideas that you get in particle physics where you can describe what's going on and connect it to other ideas. That's also really beautiful.
Mm-hmm.
I think basically insights can be beautiful. They might seem simple, but sometimes they genuinely are. And sometimes they're built on a whole system that you have to understand before. I mean, if you actually saw Einstein's equations written out in components,
Mm-hmm.
you wouldn't think it's so beautiful. You write it in a compact way. It looks nice.
What do you think about the successes and the failures of string theory? To what degree do you think it's succeeded? To what degree is it not succeeded yet or has failed?
I think to talk about any science in terms of success and failure often misses the point because there's not some absolute thing. And I do think that string theorists were a bit overly ambitious, not overly ambitious, but a little bit overly arrogant in the beginning, thinking they could solve many problems that they weren't going to solve. That's not to say the methods and advances in string theory don't exist. But they certainly weren't able to immediately solve all the problems they thought they could solve. But it has given us tools. It has given us some insights. But it becomes almost a sociological question of like how much it should be one or the other. I do think that you can get caught up in the problems themselves, and sometimes you can get caught up in the methods and just sort of do other examples. Mm-hmm. So the real physics insights often come from people who are thinking about physics as well as the math.
Because you mentioned AI, is there hope that AI might be able to help find some interesting insights? I mean, another way to ask this question is, how special are humans that we're able to discover novel insights about the world?
That's a great question. And it depends on what kind of insights, and we're going to find that out. I mean, it's because it's hard to think about something that doesn't quite exist yet. I mean, I could just think about something, take a step back. It's a little bit like to understand 4 dimensions, you go back to 3 dimensions, so to go to something you can imagine. So you can sort of say a lot of the things in a very different level about the internet. You could say, has the internet helped do things? And that's, it definitely took on a life of its own in some sense, but it's also something that we're able to tame. I know that I myself wouldn't have been able to write books if the internet didn't exist, because I wouldn't have had the time to go to the library and look everything up. And it helped me enormously. And in some sense, AI could be that in a very nice world. It could be a tool that helps us go a step further than we would and a lot more efficiently. And it's already done that to some extent. Or it could be like the parts of the internet that we can't control, that are ruining politics or whatever. So, and there's certainly a lot of indications it can do that. Then there are even bigger things that, people speculate about AI being able to do its own things. But in terms of actually figuring things out, we're in the early stages.
Yeah, there's several directions here. One is like on the theorem prover side, so Wolfram Alpha, where everything is much more precise. And when you have large language model type of stuff, one of the limitations of those is it seems to come up with convincing looking things,
Mm.
which we don't know if it's true or not.
Right.
And that's a big problem for physics.
So large language models are more or less like generalizations of stuff that we have. So the question is, so there's still breakthroughs in AI waiting to happen, and maybe they are happening, and maybe they'll be good, maybe not. But that's not quite the same. I mean, maybe in some cases, it's just pattern recognition that leads to important things. But sometimes it could be something more insightful than that I can't even put my finger on. So it forces us to, I mean, we don't really understand how smart we are. We don't understand how we think about things all that well, actually. But one thing is true, though, we're a lot more efficient right now than computers in coming up with things. We require a lot less energy to do that. So if computers figure out how to do that, then it's going to be a totally different ballgame. So there are clearly kinds of connections that we don't know how we're making, but we are making them. And so that's going to be interesting. So, I say we're in early stages, but this is changing very rapidly. But right now, I don't think that it's actually, you know, discovered like new laws of physics, but could it in the future? Maybe it can.
It will raise big questions about what is special about humans that we don't quite appreciate. There could be things that are like that leap of insight that happens, truly novel ideas that could potentially be very difficult to do.
So there are sort of abstract questions like that. There's also questions of how is it that we can address to some extent, how will AI be used in the context of the world we live in,
Sure.
which is based on, at least our country is based on capitalism and a certain political system. And how will global politics deal with it? How will our capitalist system deal with it? What will be the things that we focus on doing with it? How much will researchers get control of it? To be able to ask different sorts of questions. I mean, while it was starting out, people were doing these kind of toy problems, but what will it actually be applied to, and what will it be optimized to do? There's a lot of questions out there that it's really important we start addressing.
What to you is the most beautiful unsolved problem in physics and cosmology? What to you is really exciting if we can unlock the mystery of in the next few decades?
So is it what's the most beautiful unsolved problem, or what is the most beautiful unsolved problem I think we can make progress on?
Oh boy.
I
We
mean,
make
look,
progress on in the next few centuries.
there's most of the questions, the big questions have to do with what underlies things, how things started, what's at the base of it. There's also just basic questions like that you asked earlier, how far will science take us?
Mm-hmm.
How much can we understand? There are questions like how we got here, what underlies it, are there, but also, I mean, there's really deep questions like, what fraction are we actually seeing? Or if there are these other forces, if there is another way of seeing the world, are there universes beyond our own? If they're so totally different, how do we even comprehend them? I mean, how do we detect? Like, what would we even think about them? So there's a lot about trying to get beyond. It's always just getting beyond our limited vision and limited experience and trying to see what underlies it, both at small scales and at large scales. We just don't know the answers. I mean, I'd like to think that we understand more about dark matter, about dark energy, about are there extra dimensions, things that we actually work on. But there's probably a lot beyond what we work on that's yet to be discovered.
Yeah, understanding the extra dimensions piece will be really interesting.
Totally. I mean, if it is, how the universe went from higher dimensions to what we see, are the extra dimensions present everywhere? I mean, one of the really interesting pieces of physics we did that I talk about in my first book, War Passages, is finding out that there can be a higher dimension, but only locally do you think there's a gravity of a lower dimension. So it could be like only locally do we think we live in 3 dimensions. It could be higher dimensions is different. It's not actually the gravity we have, but there's all sorts of phenomena that might be out there that we don't know about. All sorts of evolution things, time dependence that we don't know about. And of course, that's from the point of view of particle physics. From the point of view of other kinds of physics, we're just beginning. So who knows?
Yeah, if the physics changes throughout, is not homogeneous throughout the universe, that would be weird.
I mean, for the observable universe, it's the same, but beyond the observable universe, who knows?
What advice would you give? You've had an exceptional career. What advice would you give to young people, maybe high school, college, on how to have a career they can be proud of and a life they can be proud of?
I think the weird thing about being a scientist or an academic in general is you have to believe really strongly in what you do while questioning it all the time.
Hmm.
You can't, and that's a hard balance to have. Sometimes it helps to collaborate with people, but to really believe that you could have good ideas at the same time knowing they could all be wrong, that's a tough tightrope to walk sometimes.
Mm-hmm.
But to really test them out. The other thing is sometimes, if you get too far buried, you look out and you think, oh, there's so much out there. And sometimes it's just good to bring it back home and just think, okay, can I have as good idea as the person next to me rather than, the greatest physicist who ever lived. Mm-hmm. But right now, like you said, I think there's lots of big issues out there and it's hard to balance that. And sometimes it's hard to forget the role of physics. But I think, Wilson said it really well when he said, when they were building Fermilab, it was like, this won't defend the country, but it'll make it worth defending. There's just the idea that, in all this chaos, it's still important that we still make progress in these things. And sometimes, when major world events are happening, it's easy to forget that. And I think those are important too. You don't want to forget those, but to try to keep that balance because we don't want to lose what it is that makes humans special.
So that's the big picture. Would you also lose yourself in the simple joy of puzzle solving?
Yeah. I mean, we all like solving puzzles. And actually, one of the things that drives me in my research is the inconsistencies. When things don't make sense, it really bugs me. And I just will go into, different directions to see how could these things fit together.
So it bugs you, but that motivates you.
Yeah, totally.
Until it doesn't.
Because I think, I have this underlying belief that it should make sense, even though the world comes at you in many ways and tells you nothing should make sense. But if you believe that it makes sense, then you look for underlying logic. And I think that's just good advice for everything, to try to find why it is the way it is. I think, I talk about effective theory in my second book, Knocking on Heaven's Door, a lot. It's sort of, rather than ask the big questions, sometimes we just ask the questions about the immediate things that we can measure. Mm-hmm. And we can, like I said, we can sometimes tell one that will fail, but we can have these effective theories. And sometimes I think, when we approach these big questions, it's good to do it from an effective theory point. Why do I find this satisfying? Why is the world we have the way it is? We think things are beautiful that we live in. I mean, I'm not sure if we had different senses or different ways of looking at things, we wouldn't necessarily find it beautiful. But I have to say, it is kind of fantastic that no matter how many times I see a sunset, I will always find it beautiful. Mm-hmm. It's like, I don't think I ever see a sunset and say, whatever. Mm-hmm. It's just always beautiful. You'll always, and so there are things that as humans, clearly resonate with us, but, we were maybe evolved that way. But that's about us. But in terms of figuring out the universe, it's kind of amazing how far we've gotten. We have discovered many, many wonderful things. But there's a lot more out there. And I hope we have the opportunity to keep going.
And with effective theories, one small step at a time. Just keep unraveling the mystery.
But also having in mind the big questions, but doing one small step at a time. Exactly.
Yeah, looking out to the stars. You said the sunset. For me, it's the sunset, the sunrise, and just looking at the stars. It's wondering what's all out there and having a lot of hope that humans will figure it out.
Right. I like it.
Lisa, well, thank you for being one of the humans
well,
in the world
having me here.
For that are pushing it forward and figuring out this beautiful puzzle of ours. And thank you for talking today. This is amazing.
Thank you.
Thanks for listening to this conversation with Lisa Randall. To support this podcast, please check out our sponsors in the description. And now, let me leave you with some words from Albert Einstein. The important thing is to not stop questioning. Curiosity has its own reason for existence. Thank you for listening and hope to see you next time.